Hi there. I'm glad you've slipped into this little pocket of quiet with me. Outside, the universe is unfolding in every direction, stars being born, worlds circling in the dark, and perhaps, somewhere far beyond our own sky, other eyes looking back with the same quiet questions. Tonight, we're going to drift outward together, past the familiar glow of our sun, and into the deep dark ocean between the stars, following a simple, gentle curiosity. Where might life find a way to exist out there? And what would it mean for us if it does? We'll move slowly, letting possibilities open like distant constellations. No rush, no pressure, just a soft wander through cosmic neighborhoods that might cradle oceans, atmospheres, or something stranger. If these calm journeys into the dark help you rest or keep your thoughts company, a quiet like and a gentle subscribe help others find their way here too. For now, just listen. Space is waiting. From the moment people first understood how vast the cosmos is, a gentle question has followed us. Are we truly alone out here? Somewhere beyond our familiar sky, could there be other kinds of life, growing quietly under strange suns, on shores no human has ever seen? For a long time, that question stayed in stories and whispered thoughts at night. Then our curiosity found tools. Telescopes turned toward the dark, catching faint pinpoints of distant light. Rockets pushed small machines away from Earth, and they began to circle other worlds, sending back pictures and a deeper sense of how wide our neighborhood really is. One of the first places this question settles is close by, on a world we have watched for centuries. In most images, it looks dry and cold, a rust-colored sphere against black space. But if you let time roll backward in your mind by a few billion years, that world changes. The air thickens with carbon dioxide. Heat lingers under the heavy sky. Water gathers on the surface and starts to move. Rivers cut channels through rock. Lakes spread into low-lying basins. A broad ocean may have covered much of the northern hemisphere, its surface dim under thin, hazy clouds. Now, almost all of that water is gone from view. What remains are traces. The planet's magnetic field was always weaker and less stable than Earth's, and over long ages that made it harder to hold on to a thick atmosphere. The steady stream of particles blowing outward from the sun pushed into the upper air and slowly stripped it away. Sunlight broke water vapor apart into hydrogen and oxygen. The light hydrogen slipped into space and did not return. The heavier oxygen stayed behind, combining bit by bit with minerals in the rocks. Dark surfaces turned reddish as iron oxidized. Dust from those rocks spread over the ground, laying down the fine orange layer that now covers so much of the planet. Most of the remaining water is believed to be frozen. Some lies buried in the soil as ice mixed with dust and stone. In many regions, the ground itself may be permafrost, hard and dry on top, but icy below. Seen from orbit, the planet's face is crossed by winding channels that look exactly like empty riverbeds. They branch and merge, curve around obstacles, and fan out as they approach lowlands. Even without liquid water, the shapes tell you what once flowed there. To understand how such a change could happen, it helps to look inside the planet as well as at its skin. A lander named InSight spent years listening for tiny tremors in the ground. Each small Marsquake sent waves through the interior, and by watching how those waves moved, scientists could infer the layers hidden below. At the center lies a dense core of iron with some sulfur and nickel mixed in, more than half the planet's radius in size and extremely hot. But heat alone is not enough. Deep in that core, the pressure is so great that much of the material is thought to be stiff rather than freely flowing. On Earth, moving metal in the outer core helps generate a strong global magnetic field. On this world, with a quieter, more rigid core, the magnetic field cannot stay strong for long. Around the core is a mantle of rock, partly molten and slowly creeping over very long timescales. Deeper parts of this mantle are richer in heavy metal oxides, while higher regions are made mostly of silicate minerals, such as olivine. Outside the mantle lies the crust, a solid shell that wraps the planet. Here, that shell is thick, on average about 50 kilometers deep. That is far more than the typical ocean floor on Earth, and closer to the thickness of our continents. A crust that thick suggests a world that cooled and stiffened early, making it harder for the surface to renew itself. There is also a quiet difference between north and south. In the north, the crust is dominated by lighter andesite-like rock. In the south, darker basalt is more common. It is as if two large chapters of the planet's history were written under slightly different conditions and then preserved side by side. Orbiters have been mapping this outer shell for many years, building up a detailed view of craters, plains, volcanoes, and old river systems. Among the most dramatic features is a vast scar near the equator, a complex of canyons and chasms so long and deep that, if it lay on Earth, it would stretch across entire continents. This system, called Valles Marineris, runs for thousands of kilometers. Sheer cliffs rise from its floor, and side valleys split and twist away into the distance. At the western end of this rift, the canyons cut into a great volcanic plateau built from ancient lava flows. Near the middle of that highland lies a region where the ground seems to have come apart in a particularly tangled way. It is called Noctis Labyrinthus, the labyrinth of night. From above, it looks like a maze of deep trenches and isolated blocks, extending for more than 1,000 kilometers from west to east. Pieces of the crust appear to have dropped downward along fractures, forming tall mesas separated by narrow, steep-walled corridors. The tops of these blocks are capped with softer, lighter-colored deposits, worn by time into rounded forms. Their sides expose harder, older bedrock. Over billions of years, parts of the steep walls have broken and slumped, collecting as landslides at the base. Long ago, rain or snow that fell on the nearby highlands may have drained into these fractures, turning them into passageways for flowing water. The floor of many troughs bears streamlined shapes and grooves that match what fast-moving water leaves behind. Layers in the exposed walls and in the landslide material mark cycles of settling sediments, periods when material was laid down, then eroded, then laid down again. When the reflected light from this region is broken into its component colors, certain minerals stand out. Some, like hematite, are iron oxides that commonly form in water. Others resemble opal or sulfate salts, which also need liquid water at some stage of their history. Together, they quietly point to repeated contact between rock and water in this place long ago. Even today, in air that is thin and cold, Noctis Labyrinthus behaves a little differently from the open plains around it. Observations suggest that fog often gathers here. During the day, a small amount of water stored in the upper soil can warm and escape as vapor. The high canyon walls help hold this moisture in place. As evening comes and temperatures fall, that vapor cools and condenses into tiny ice crystals. A low, fine mist forms, then settles as frost on the rocks and dust, a fragile film of ice that may vanish again with the next sunrise. Traveling eastward along the canyon system, the tightly interwoven chasms gradually open into broader valleys. Each has its own details, but nearly all of them carry the marks of two slow, patient forces: water in the deep past and wind in the long, dry time that followed. Large floods may once have surged through these channels, cutting deeper into the bedrock and moving great amounts of sediment. After the climate changed and surface water disappeared, wind-blown sand and dust continued the work of erosion, smoothing sharp corners and spreading a thin layer of loose material across the floors. Farther along, the canyons lead toward one of their most dramatic basins, known as Socrates Chasma. Here, the canyon floor drops to one of the lowest points in the entire system, many kilometers below the surrounding plateau. If you stood on the edge and looked down, the depth would far exceed any cliff on Earth. From its shape, scientists infer that this basin may once have held a long, narrow lake, dark and cold beneath a heavier ancient atmosphere, comparable in volume to some of our own inland seas. Sediment settling at the bottom of such a lake would have built up in thin layers over long spans of time. Each layer could hold information about the water that placed it there, the temperature, the chemistry, even whether tiny organisms were present. If simple life ever found a foothold in that lake, traces of it might still rest in those protected sediments, shielded by overlying rock and dust after the water vanished. The canyon walls surrounding the basin display bands of different colors and textures stacked one above another like the pages of a geologic book. Beyond this deep reach, the canyon system grows shallower and wider. The high cliffs slowly ease into lower slopes, and the great rift opens out into a broad plain called Planitia. Even there, where the landscape is smoother, the memory of moving water lingers in the shapes of the ground. Terraces step downward toward the lowlands, as if marking different high stands of ancient floods. Long ridges rise like islands from the surrounding plain, with gentle slopes on the side that once faced the flow and sharper tails pointing downstream. On Earth, forms like these appear in the deltas and outwash plains of major rivers, where water slows and lets go of the sediment it has carried. Seeing such familiar patterns on this distant, rust-colored world is like hearing a faint echo of a landscape you know. It hints that immense volumes of water once burst out of the canyon system and spread across these lowlands before seeping away, freezing, or drifting off as vapor. Taken together, the canyons, chaotic terrains, ancient lake basins, and flood-shaped plains trace one of the clearest stories this planet has to offer: that it was once far wetter and more active than it is now. In the cliffs of Valles Marineris, in the frosts of Noctis Labyrinthus, in the buried layers of Planitia, there is room for both memory and possibility. The memory of old rivers and quiet lakes, and the possibility that, for a time, life may have found a way to exist there, small and fragile under a distant Sunday. For now, though, we can only follow that story from above. From orbit, the great rift of Valles Marineris still looks like a wound in the planet's skin, a place our machines have mapped with care but never touched with their wheels. In imagination, we drift along its length, and then gently let our path swing eastward, gliding away from the shadowed canyons, across old highlands, and down over stony plains until another shape slowly rises beneath us. A round basin with a solitary mountain standing in its center. This is Gale Crater. Long ago, an asteroid struck here with tremendous force, carving a deep bowl in the crust and lifting a central island of shattered rock. Over ages, wind and water softened that island, wrapping it in layer after layer of sediment, until it became the stepped mountain we now call Mount Sharp. In the crater's early days, water likely pooled inside this basin, forming a lake that lasted far longer than any flood. Fine material carried by streams and storms settled quietly to the bottom in thin sheets, each one a page in a slow story about air, water, and time. Today, Gale is more than an ancient scar. It is also home to a small traveler from Earth. In August 2012, a car-sized rover named Curiosity was lowered to the surface and set gently on its wheels. Its purpose was simple and deep: to find out whether this planet once offered environments that could have supported life, even if only as tiny microbes. Almost at once, the landscape began to answer. Curiosity's first images showed rounded pebbles pressed into a hardened surface that looked very much like an old stream bed. The rover had come down near the remains of an ancient channel where a lively stream once rushed by. That region was given a quiet name, Peace Vallis, the Valley of Peace, a reminder that water really had moved through this place. Curiosity's first careful steps took it into a patch of rippled sand called Rock Nest. There, it scooped up a small amount of soil and fed it into its internal laboratory. Even this dry-looking dust held a measurable fraction of water locked into the minerals. From Rock Nest, the rover rolled toward a region called Glenelg, where different kinds of rock meet. Harsh winds had stripped some areas down to very ancient bedrock. Nearby, younger deposits lay on top, preserving traces of calmer times. As Curiosity crossed this patchwork, it paused often to drill shallow holes and examine the fine layers inside, layers that had been sealed away for billions of years. Step by slow step, it approached the base of Mount Sharp, weaving between rocky rises and skirting dark dunes. At the edge of a dune field known as the Bagnall Dunes, it studied both the restless sand and the solid rocks beside it. The dunes, still sculpted by thin winds, showed how the surface continues to change even now. The layered rocks nearby told of water that had stood or flowed here long before the dunes took shape. Ahead lay a low ridge later, named for astronomer Vera Rubin. As Curiosity climbed onto this ridge, its instruments began to detect more and more hematite, an iron mineral that often forms where water and rock interact. The ridge appeared to be rich in materials laid down in watery settings, perhaps along an ancient shoreline or on the floor of a shrinking lake. Piece by piece, a gentle but powerful picture emerged. Gale Crater once held stable bodies of water, not just brief, violent floods. Clay minerals, fine mudstones, and subtle textures all pointed to a lake that could have been calm and long-lasting enough to be welcoming to simple life. If such life ever existed here, Curiosity kept traveling long past the mission's original plan. Built to last for a couple of Earth years, it has endured dust storms, rough ground, and the slow grinding of time. Day after Martian day, it has driven a little farther, stopped to measure, then rolled on. Over thousands of days, it has covered tens of kilometers, a slow pilgrimage across an alien basin. Along the way, it has drilled into rocks and heated the powdered samples, reading the light they give off to learn their composition. Those experiments revealed organic molecules, carbon-bearing compounds, such as benzene and other ring-shaped hydrocarbons. These do not prove that life was present, but they show that early Mars contained some of the raw ingredients from which living chemistry can be built. The planet was not empty in its possibilities. It held building blocks, mixed into mud and stone beneath a thicker, warmer sky. If your thoughts drift farther southwest from Gale, the surface drops away into an even broader depression, a basin so wide and deep that it shapes an entire region of the planet. This is Hellas Planitia, one of the largest impact craters in the solar system. Around 4 billion years ago, a massive asteroid came in at high speed and struck here. The impact excavated a hole more than 1,000 kilometers across and flung huge amounts of rock outward, perhaps even launching some fragments briefly into space before they fell back across Mars. In those early, wetter times, this low basin would not have stayed empty. Water from rivers and underground sources would have flowed downhill into the hollow. For a while, Hellas may have held a deep lake or inland sea, its shores lined with terraces and deltas where incoming streams dropped their sediments. As the climate cooled and dried, that water gradually drained away, froze, or vanished into the thin air, leaving the basin colder, dustier, and quieter. From orbit, the floor of Hellas looks smooth and pale, like a flat plane. Closer views show that it is softly wrinkled with low hills, ridges, and cracks. Many of these shapes are thought to come from ice hidden underground, mixed with dust and rock, making the surface sag and fracture in patterns that echo certain Arctic landscapes on Earth. Because Hellas lies so deep below the planet's average level, the air at its bottom is denser. Mists sometimes pool within the basin, softening the view with a hazy brightness, unusual for Mars. During the long southern winter, Hellas can be coated in frost and seasonal ice. Seen through a telescope, the basin shines as a bright spot against darker surroundings, a deep, ancient wound that happens to catch the winter light. Far to the north of Hellas lies another crater that has drawn special attention, not because of its size alone, but because of what is preserved inside. This is Jezero crater. In the distant past, it held a lake fed by at least 2 rivers. One flowed from the north, another from the west, each cutting channels through the highlands. Where the western river entered the crater, it slowed and spread out, dropping sand and silt to build a fan-shaped delta with branching lobes and layered deposits. Those fossil deltas still stand today, frozen mid-flow. Their shapes make Jezero one of the most promising places on Mars to search for traces of ancient habitability. On Earth, fine muds in such deltas are wonderful at trapping and preserving tiny signs of life. If living things ever flickered in Martian lakes, their traces might still be hidden in these soft, layered sediments. Because of that promise, Jezero was chosen as the landing site for another rover, Perseverance. In February 2021, it arrived at Mars and descended toward the crater. The plan was to set it down near an area called Three Forks, close to the old delta. But thin air and shifting winds nudged the spacecraft slightly aside, and it landed safely a short distance away, separated from its intended path by rough ground and sand-filled hollows that would be risky to cross. Perseverance did not arrive alone. Fastened to its belly was a small experimental helicopter named Ingenuity. After the rover settled in, Ingenuity unfolded and took to the air on slender blades, becoming the first aircraft to fly on another planet. Flight by careful flight, it rose into the thin air and skimmed over the surface, taking wide-angle images of the terrain ahead and helping mission planners choose safer routes. Meanwhile, Perseverance began its own slow trek. It drove along the safer margins of the hazardous area, stopping to study outcrops and to drill slender cores from selected rocks. Each core was sealed in its own small metal tube, tucked away as a future gift samples that another mission may one day bring back to Earth. Looping around the northern side of the dangerous sands, the rover gradually curved westward toward the fan of delta deposits and rolled up onto the ancient lake bed. Since then, Perseverance has built a growing collection of rock cores and soil samples, each one a sealed time capsule from billions of years ago. Its instruments measure textures, minerals, and chemistry, looking for patterns that hint at past habitability. Among its experiments is a device called MOXIE, designed to take in the carbon dioxide that fills the Martian air and split some of it, producing small amounts of pure oxygen, a quiet test of how future explorers might make part of their air or fuel from the atmosphere itself. All the while, Ingenuity has continued to fly. Originally planned for just a few test hops, it has gone on to complete many more. Each short journey shows again that even in an atmosphere less than 1% as dense as Earth's powered flight is possible, and that one day light, agile scouts may slip easily over cliffs, valleys, and broken ground that wheeled rovers could never safely cross. When you picture these two robots, the steady rover and its slight, whirring companion moving together across the floor of an ancient lake, there is a quiet tenderness in the image. They are tiny and mechanical, far from home, yet they carry within them a very human patience and curiosity. Step by step, flight by gentle flight, they help us ask the old question in a new way. If life once touched these waters and sediments, how might its story still be written in the stones beneath their tracks? Every so often, in the pauses between those careful steps, Perseverance turns its attention away from the ground. Its cameras lift from rocks and ripples of sand and look up. Even under that thin, cold sky, there are companions moving through the dark. On some nights, a pale dot drifts slowly over the horizon, one of Mars's tiny moons. On another day, the rover watched a darker shape cross in front of the sun, nibbling at its bright disk for a few brief moments. It was seeing an eclipse, not caused by a large, neat moon like ours, but by a lopsided little world circling close to the planet. Mars has two such moons, Phobos and Deimos. They are nothing like the round, bright moon that lights our own nights. Instead, they are small and misshapen, more like rugged asteroids that have somehow taken up residence around a planet. When you look closely at them in images from orbiters, you see surfaces heavily pitted with craters, covered in gray, dusty powder that softens their outlines. From the way they reflect light and the signals they send back in different wavelengths, Phobos and Deimos seem to resemble dark, carbon-rich asteroids. That has led many scientists to wonder if they began life far from Mars, in the belt of debris between Mars and Jupiter, and were later drawn in and captured. In that picture, a primitive, fragile body wandered too near the red planet. Tidal forces may have stressed and fractured it, breaking it into pieces that eventually settled into separate orbits. Over time, only the largest fragments remained, the two moons we see today. Another story imagines a different kind of beginning. Very early in the solar system's history, a large protoplanet may have struck young Mars in a glancing, catastrophic blow. Rock and molten material were blasted into space, forming a temporary ring of debris around the planet. Gently, under the pull of gravity, that material clumped together into a few small moons. If that tale is true, Phobos and Deimos would not be visitors from far away at all, but children of Mars itself, built from its own scattered crust and mantle. For now, the evidence does not settle firmly on one origin or the other. The moons keep their secrets a little longer. turning quietly above the rust-colored deserts. Phobos, the larger of the two, circles close to the planet, so close that some human-made satellites around Earth actually orbit farther from us than Phobos does from Mars. Yet, it is so modest in size that if you were standing on the Martian surface beneath its path, it would look smaller than our moon appears in our own sky. It would rise and set quickly, hurrying from horizon to horizon in a matter of hours. Despite being made of rock and rubble, Phobos is strangely light. Its average density is low enough that a large fraction of its interior must be empty space. Instead of being a solid, unbroken sphere, it is probably a loose collection of fragments held together by their own weak gravity, what astronomers sometimes call a rubble pile. Inside, there may be voids and pockets where the pieces do not quite fit tightly together. Living so close to Mars comes with a cost. Tidal forces, the same kind of stretching pull that raises ocean tides on Earth, are gradually tugging Phobos inward. With every passing century, its orbit shrinks by a small but measurable amount. We cannot see the change from one night to the next, but over millions of years, it adds up. Far in the future, Phobos is expected to cross a line where the stresses become too strong. The moon may fracture, spreading into a ring of debris around Mars, and eventually, that material will spiral downward, streaking through the thin air and falling to the ground as a long, slow rain of stone. Deimos, the smaller moon, is in a gentler situation. It travels farther out, on a nearly circular path that is slowly drifting away from Mars instead of toward it. Deimos is darker than dark, absorbing most of the sunlight that reaches it. Its surface reflects so little light that, even above the thin Martian air, it shines only modestly. From the ground, it does not show a visible disk to the naked eye. It looks more like a bright star moving in a predictable path, easy to mistake for a distant point of light if you did not know what you were watching. If you could stand near Perseverance on a clear evening and look up, you might see Phobos rise in the west and race overhead, while a little later, Deimos glides along a slower, higher track. Both moons move in the same direction around Mars, but their different distances create a subtle illusion when seen from the surface. Their motions cross and weave in the sky like two insects flying at different heights, each following its own invisible circle. These small, irregular moons may not seem like likely homes for life, but they are important in another way. By watching how they move, how they tug on Mars and on each other, scientists learn more about the interior of the planet and the history of its orbit. By studying their composition, we gather clues about the early days of the solar system, when impacts and captures were more common, and worlds were still trading pieces of themselves through violent encounters. If you let your thoughts drift outward from Mars, past its modest moons, and into the darker cold beyond, another presence slowly comes into view. Far from the sun, wrapped in wide rings of ice and dust, Saturn turns with a serene, pale light. And circling this planet, at a distance where sunlight feels thin and bluish, there is a moon that holds a special kind of mystery, a world called Titan. Titan orbits Saturn at a distance of more than 1 million kilometers, taking a couple of weeks to complete each slow circuit. It is Saturn's largest moon, bigger even than the planet Mercury, though it is much lighter. That low weight for its size tells us that Titan cannot be made mostly of heavy rock and metal the way Earth and Mercury are. It must be built from a different balance of materials, a mixture of rock, ice, and other frozen substances layered together. Deep inside Titan, models suggest a compact rocky core made of silicate minerals presses inward under its own gravity. Around this core lies a thick shell of high-pressure ice, and, above that, a global ocean of liquid mixed with things that would be exotic seas to us: water blended with ammonia, methane, and various salts. These extras lower the freezing point of the liquid, allowing it to remain fluid even at temperatures far below the freezing point of pure water. Above the hidden ocean is a stiff crust made of water ice and a crystalline form of methane and water, known as methane hydrate. This crust may be tens to more than 100 kilometers thick. It is not perfectly rigid. The changing pull of Saturn flexes it ever so slightly, raising and lowering broad regions over long timescales. Those tidal flexes can fracture the crust, creating cracks and faults that give cold interior material a path toward the surface. Where that material reaches the open air, it can erupt not as molten rock, but as slurries of water, ammonia, and other volatiles, a kind of cryovolcanism, volcanism made of cold. Geysers and domes, if they exist in active form, would pour out substances that quickly refreeze into ice, or spread as flows that harden into frozen plains. Among these erupting ingredients, methane plays a special role. On Titan, methane behaves a little like water does on Earth. The surface is so cold, around minus 180 degrees Celsius, that water is locked up as hard rock, but methane can shift between gas and liquid. Gentle changes in temperature and sunlight can make methane vapor condense into tiny droplets. Clouds form in the thick air. Eventually, those droplets become heavy enough to fall as rain, not of water, but of liquid hydrocarbons, splashing into rivers and collecting in lakes and seas. Images from spacecraft have revealed dark, glassy patches near Titan's poles, large lakes and seas filled with liquid methane and ethane. River channels snake into them, carved through pale, icy ground. On some days, hazy clouds build up and drift, hinting at ongoing weather. Over seasons, the rain may move from one hemisphere to the other, wetting some regions while others dry out, all within a cycle based not on water, but on methane. Wrapping all of this is Titan's thick atmosphere, richer and more layered than that of any other moon we know. It is made mostly of nitrogen, like Earth's air, with a small share of methane and traces of more complex organics. The air is dense and cold, pressed close to the surface in a deep, hazy blanket. Sunlight filtering down through this atmosphere meets methane high above the ground. Under the influence of solar radiation and charged particles from Saturn's magnetic field, methane molecules are broken apart and recombine into longer, more complex chains. Those chains of carbon and hydrogen and small bits of nitrogen mixed in form microscopic particles called tholins. They drift downward like a slow, steady dust, giving the air its characteristic orange-gold color. Layer upon layer of this photochemical smog hides the surface from a casual glance, making Titan look soft and featureless when seen in ordinary light from far away. Beneath that veil lies a world shaped by forces that echo our own, yet built from utterly different materials. Dunes sculpted from grains of ice, valleys carved not by water, but by liquid methane, rounded hills that may be cryovolcanic domes, and smooth plains gathered around dark polar seas. At first glance, the shapes look familiar, like memories of deserts and coastlines on Earth, but the substance of everything is changed. Rock is ice, rain is methane, and the haze above holds the simple molecules that feed complex chemistry. It sits far beyond the sun's warm embrace, well outside the traditional habitable zone, where liquid water should scarcely exist. And still, something about Titan feels quietly restless, quietly promising, as if the ingredients that once guided life on our own world are rearranging themselves here in a different key. High above those frozen plains, the haze that blankets Titan takes on a steady, golden glow, a twilight that never quite lifts. Tiny particles drift in layers, absorbing most of the sunlight that tries to reach the ground, and scattering the rest across the sky until everything below is muted, softened, dreamlike. Yet, for all its thickness, that same veil is gentle toward another kind of light. Infrared rays, longer, deeper, patient, slide through it more easily, carrying back faint hints of what lies beneath. In those dim, filtered echoes, we begin to trace the outline of a world that is cold, strange, and somehow full of possibility. This thick, light-eating blanket does something unusual to Titan's climate. On Earth, clouds and greenhouse gases tend to trap warmth and keep the surface from losing its heat too quickly. On Titan, the upper haze blocks a great deal of incoming sunlight before it can ever warm the ground, while the lower atmosphere still lets some of the heat that does arrive leak away. The result is a kind of anti-greenhouse effect. The surface ends up colder than it would be without that veil, chilled by several more degrees in a world that was already deeply frigid. The haze makes Titan hard to explore with simple cameras. In visible light, the moon's face looks smooth and featureless, wrapped in a uniform amber glow. But the Cassini spacecraft, which spent years circling Saturn, carried instruments that could see in infrared. Those eyes, tuned to the wavelengths that slip between the haze particles, slowly piece together a map of Titan's hidden surface. It is enough to show that this is not a bland world at all. Under the fog, contrast is everywhere. Broad regions reflect light differently. Some patches are bright, telling of icy highlands or exposed bedrock. Others are dark and muted, where organic sands or liquid hydrocarbons have gathered. Near the equator, slightly to the south, lies one such striking area, a complex terrain often associated with towering structures and deep hollows. Here rises one of Titan's great mountains, Doom Mons, swelling upward from the surrounding plains until it stands more than a kilometer above them. Doom Mons is not a sharp, rocky peak like those carved by erosion on Earth. Instead, it spreads wide, tens of kilometers across its flanks, built up by repeated outpourings of material from below. At its summit and along its upper slopes, shallow depressions and calderas hint at past eruptions. The flows that stream outward from its sides look relatively fresh in radar images, with smoother textures and clearer boundaries than the older terrain around them. Rather than molten rock, these eruptions likely involved slushy mixtures of water, ice, ammonia, and other volatiles, which would have gushed out, spread, and then frozen into gently rolling, solid forms. In that sense, Doom Mons is thought to be a cryovolcano, a volcano of cold. Just to the northeast lies a darker, deeper scar in Titan's crust, a long, steep-walled depression often called Sotra Patera. It stretches for dozens of kilometers, with a floor that sinks roughly 2 kilometers below the surrounding landscape. Its shape and its close association with Doom Mons suggest that it may be part of the same restless system, perhaps the drained throat of an ancient cryovolcanic vent. Together, the mountain and the neighboring pit form what seems to be a single, large tectonic and volcanic complex, frozen in mid-story. North of Doom Mons spreads a wide, irregular swath of terrain, known as Mohini Fluctus. In the dim, grainy radar views, this region looks like a frozen sea caught in motion. Long, lobed flows of material extend outward, overlapping and weaving around each other, as if wave after wave once rolled away from the source and stiffened where they came to rest. Between these flows, darker stripes and patches mark extensive dune fields, where winds have piled up grains of solid hydrocarbons and ice into sinuous ridges. In some places, the flows narrow, only a few kilometers across. Elsewhere, they spread to dozens of kilometers wide, forming a patchwork of pale, frozen lava and darker, rippling sand. Drifting on, the view shifts to another kind of scar, an ancient impact crater, so large that it dominates its part of the moon. This is Minerva, Titan's biggest known crater. From rim to rim, it measures hundreds of kilometers, but its depth is surprisingly modest, only a couple of hundred meters from the surrounding uplands down to the floor. The ring of mountains that marks its outer edge rises less than half a kilometer above the plains. Minerva's soft profile tells a quiet story of age. Over hundreds of millions to more than 1 billion years, erosion by liquid hydrocarbons, slow settling of icy crust, and perhaps subtle tectonic shifts have worn the crater down. Small channels cut across its rim. Deposits have spread across its interior. In sharper relief, you can still see its structure, a lighter central region encircled by a darker moat, and then a low outer ridge. Compared to fresh craters on airless bodies, its edges are blurred, its features subdued. The only reason it still stands out at all is its sheer size. From Minerva, the land below seems to gather itself again into something stranger. Farther south lies a bright, curved feature that arcs across the surface for hundreds of kilometers. Seen from above in Cassini's radar data, it looks like a glowing brushstroke on a darker canvas. This is Haute Arcus, a unique, arc-shaped region that marks a boundary between rugged uplands to one side and lower, more subdued plains to the other. Along this arc, textures and brightness change sharply. Some portions appear to shift in reflectivity over time, brightening or dimming between observations. That has led scientists to suspect that something in this region may still be active, at least occasionally. Fresh deposits from cryovolcanic eruptions could dust the surface, altering how it scatters and absorbs radar and infrared light. Liquid released from below might briefly flow into nearby lowlands before freezing or evaporating away, leaving behind a new, thin layer of material. In this way, Haute Arcus may be a place where Titan's surface and interior still talk to each other now and then. From the bright curve of Haute Arcus, subtle channels extend outward toward the northwest, like pale threads etched into the landscape. In images, they resemble dry riverbeds, winding their way down slope from highlands into lower country. Along their path lies Xanadu, one of Titan's most intriguing regions, a large, bright, and rugged terrain, heavily dissected by valleys and cut by ridges. The northwestern edge of Xanadu is lined by a series of mountain chains collectively known as Mithram Montes. These ridges run roughly parallel for over 100 kilometers, their peaks rising nearly 2 kilometers above the surrounding ground. Among them stands Titan's highest known summit, reaching a little more than 3 kilometers into the thick, cold air. If you could stand on that crest and look westward, the view would open onto a wide, dark plain that stretches for hundreds of kilometers, a region called Shangri-La. Shangri-La is one of Titan's great dune seas. Much of it lies at slightly lower elevation than the bright highlands and is covered in long, parallel bands of dark material. Those are dunes, built from grains of solid hydrocarbons and water ice, organized by steady winds into ribbons that march across the surface. Between them, lighter patches poke through outcrops of older, higher ground that may once have been islands rising from a broad sea of liquid methane. The idea that Shangri-La could have been flooded in the past is supported by more than imagination. Its low altitude, smooth expanses, and the shapes of some of its boundaries hint that liquid may have lingered here, ponding in hollows and basins. Even if the surface looks mostly dry today, it is possible that liquid hydrocarbons still reside in the subsurface, seeping through porous layers the way groundwater does on Earth. West of Shangri-La lies a brighter upland region, standing out clearly against the darker dune fields around it. In radar images, it appears cut by a dense network of branching channels and valleys, as if it has been heavily worked on by flowing liquids. These features suggest that, at times, rain of methane and other hydrocarbons may have been abundant here, carving paths through the icy crust and feeding downstream basins. Some channels appear to end in low, dark areas that could once have been small lakes or marshes in Titan's strange, cold sense. Farther west still, the terrain drops into another dark lowland, a broad expanse where dunes and smooth plains blur together. To the east, near the edge of Shangri-La, lies a place with a special meaning for us, the Huygens landing site. In 2005, a small probe detached from Cassini and descended through Titan's hazy atmosphere, falling for hours on a parachute before touching down gently on the surface. As Huygens dropped, it sent back views of layered haze, then of the surface slowly coming into focus, branching channels, pale highlands, and darker plains. Its instruments tasted the air, measured the cold, and felt the firmness of the ground beneath it. When it landed, the probe settled into material that behaved a little like damp sand or soft clay, likely a mix of water ice grains and complex organic particles, moistened by traces of liquid hydrocarbons. For a short time in that distant cold, a human-made object sat quietly on the shore of Titan's ancient stories, listening to the wind and looking out over a world of frozen water and liquid methane. Through Huygens and Cassini together, the hazy mystery of Titan's face became something more familiar, not because it is like Earth, but because its patterns mountains, valleys, lakes, dunes echo shapes we know. Under an orange sky, with rocks made of ice and rain made of methane, it offers a reminder that even in places far outside a comfortable zone, nature finds ways to write landscapes in rhythms we can still recognize. High above the rings of Saturn, two companions once traveled together, the Cassini orbiter and the small Huygens descent probe tucked against its side. They left Earth in 1997 and spent 7 quiet years crossing the dark before. In 2004, Cassini slipped into orbit around Saturn. Not long after, in early 2005, Huygens was released and sent on a one-way dive toward the orange glow of Titan. Cassini stayed high, circling Saturn and listening, catching every whisper Huygens sent upward and relaying it home. Below, the little probe coasted alone until Titan's atmosphere rose up to meet it. Thin air brushed the heat shield at first, then grew thicker, slowing the craft. At a planned moment, Huygens shed its shell and opened a sequence of parachutes. For a little under 2.5 hours, it drifted downward like a seed on the wind. Sensors felt short bursts of heavy deceleration, up to 15 times Earth's gravity, but the probe held together calmly. By the time Huygens neared the surface, its speed had eased to just a few meters per second, more a firm step than a crash. It touched down, bounced once, settled, and then, in the stillness after arrival, began to send back its first close glimpses of Titan's face. The cameras looked out over a plain scattered with rounded stones and pebbles, smoothed as if they had spent a long time being rolled along by flowing liquid. The scene felt oddly familiar, like a dried-up stream bed on Earth, except that here the rocks were made mostly of water ice, and the liquid that had once shaped them was not water at all. As Huygens fell, its instruments had been quietly reading Titan's atmosphere. Tiny sensors traced the strength and direction of the winds, feeling them twist and shift with altitude. Others measured how well the air carried electric charge, hinting at layers where ionized particles gathered. Thermometers and gas analyzers sampled the air, building a profile of temperature, pressure, and composition from the high, hazy reaches down to the dim surface. A small microphone listened too, capturing the soft rush of atmosphere past the probe's hull. Once on the ground, Huygens turned its attention to the surface beneath it. A sampling device pressed into the material, drilling some 15 centimeters down. It found that beneath the thin layer of rounded pebbles lay a substrate that yielded slightly under pressure, yet held together a mix with the feel of wet sand or compacted snow. As the drill worked, instruments detected methane gas being released from the disturbed material, as if the ground were saturated with liquid hydrocarbons. The landing site, scientists later concluded, was probably much like a shallow, dried lagoon or a patch of exposed seafloor, sand-like grains made of ice and organic material, soaked or recently soaked in liquid methane and ethane. In just a few hours of life, Huygens sent back hundreds of images and a set of measurements that would quietly reshape our understanding of Titan. Careful study of that data revealed subtle but remarkable features in Titan's atmosphere. One surprise was a region of almost complete calm around 80 kilometers above the surface. There, the winds from below seemed unable to climb higher, and the currents from above did not easily reach down. It was as if the air were gently divided into two zones that mostly minded their own business, separated by this quiet band. The exact reason for such a still layer is still uncertain. Another discovery was that Titan does not have just one ionosphere, but two. High above, at altitudes of more than 1,000 kilometers, lies a familiar ionized layer, where energetic particles from the sun and cosmic rays strip electrons from molecules. Much lower, around 60 kilometers up, there is a second zone of enhanced electrical activity. Its origin is more mysterious. Perhaps complex organic molecules in the haze and subtle lightning-like discharges all play a part. Whatever the cause, Titan's atmosphere turns out to be more intricate than a single, simple blanket of air. If you let your thoughts drift northwest from the Huygens landing area, across dunes and ridges, and over the curve of the world, you eventually reach Titan's northern seas. Broad, dark patches where liquid hydrocarbons have gathered. The largest of these is Kraken Mare, a vast reservoir of methane and ethane, only slightly smaller in area than the Black Sea on Earth. Its surface is smooth and light-absorbing, like cooled oil, and where sunlight glances off at the right angle, it reflects back as a muted shimmer. Radar signals from Cassini have bounced off Kraken's surface and sometimes penetrated into the liquid, but the exact depths are hard to measure. In many places, the sea is known to be at least a couple of 100 meters deep, and likely deeper still in its central basins. It is an ocean of cold hydrocarbons, black and quiet, rimmed by frozen shores. A little farther north lies another great basin, Legia Mare. Though smaller than Kraken, it is still immense, and its composition appears to be especially rich in methane. Between these two seas stretches a long, narrow channel, a strait that connects them and allows liquid to pass from one to the other. Around and between them, dozens of smaller lakes and lagoons cluster in the polar region, their dark shapes reflecting the quiet sky. In 2014, scientists noticed something strange in Cassini's radar images of one of these northern seas. In an earlier picture, the surface had looked smooth and featureless. In a later one, a new bright patch appeared, as if an island had suddenly risen from the depths. Over the following months, the feature grew and changed shape. Then, just as quietly, it faded and disappeared, leaving the sea surface dark again. The phenomenon was nicknamed the Magic Island. One idea is that subtle changes in temperature cause layers within the sea to stir and mix. Deep below, nitrogen dissolved in the cold hydrocarbon liquid might come out of solution, forming bubbles that rise slowly toward the surface. In Kraken Mare's thick fluid, such bubbles could grow large and collect in persistent clusters. A broad field of foam, studded with reflective bubbles, would look bright to Cassini's instruments, like a temporary island that is not solid at all. As the conditions shift again, the bubbles would eventually break or be reabsorbed, and the bright patch would vanish. Other possibilities involve floating chunks of ice, waves stirred by winds, or seasonal changes in surface texture. Whatever the cause, the Magic Island hints that Titan seas are not static ponds, but active systems with their own weather and rhythms. For a time, scientists imagined sending a floating craft, a small submersible or boat, to drift on one of these alien seas, tasting the liquid directly and watching from close range as it moved. The idea remains compelling, but such a mission would be technically demanding, and for now, another plan has stepped forward. Instead of a boat, the next visitor to Titan is planned to be a flying machine, a rotorcraft called Dragonfly. Still being prepared on Earth, Dragonfly is designed as an octocopter, with 4 pairs of rotors arranged to give it both lift and stability. Power will come from a radioisotope generator, a steady, long-lived source of heat and electricity that will let Dragonfly hop from place to place for years on the frigid surface. Titan's dense atmosphere and low gravity make it, in some ways, an inviting place to fly. With the thick air providing plenty of lift, Dragonfly will be able to rise kilometers above the ground and cruise at gentle speeds across dunes, frozen plains, and ancient impact craters. On board, Dragonfly will carry cameras to take wide panoramas and close-up views of rocks, pebbles, and grains of hydrocarbon sand. A mass spectrometer will analyze samples of air and surface material, searching for complex organic molecules. Other instruments will measure weather and the mechanical properties of the ground, building a layered picture of Titan's chemistry and geology. Behind all these measurements lies a soft but profound question. Could there be, or could there once have been, some form of life on Titan? By human standards, Titan's surface looks deeply unfriendly. The temperature is far below the freezing point of water. Liquid water, the solvent that supports life on Earth, is locked into rigid ice as hard as stone. The atmosphere contains hydrocyanic acid and other reactive compounds that would be toxic to familiar biology. From this perspective, Titan seems an unlikely cradle for anything we would recognize. And yet, Titan's air and surface are rich in organic chemistry. Under the influence of sunlight and energetic particles, simple gases like methane and nitrogen are transformed into more complex molecules, nitriles, hydrocarbons. and perhaps the building blocks of nucleic acids and amino acids. On Earth, water is the great dissolver, the medium in which reactions can meet and reorganize. On Titan, liquid methane and ethane may play a similar role, albeit at much lower temperatures and with a very different set of rules. Some studies suggest that under the right conditions, mixtures of liquid hydrocarbons and compounds like phosphine can behave as a kind of primordial soup, where exotic, slow-motion chemistry might explore pathways unknown to terrestrial life. If life has found a way there, it would not look or behave like anything we know. It would be an alien in the truest sense, perhaps moving through lakes of methane or clinging to the undersides of ice grains. We do not yet know whether such possibilities are realized or whether Titan is a laboratory where only prebiotic chemistry plays. For now, it remains a world of questions and hints, of orange skies and dark seas, waiting for the next small visitor to come and listen more closely. If you let your thoughts drift outward from Titan, past Saturn's rings and the pale glow of our own sun, another, quieter kind of light begins to matter. For about a century now, Earth has been leaking radio waves into space songs, news, radar pulses, navigation signals, all tangled together in a faint, expanding shell. It is not a beacon we built on purpose. It is just what happens when a technological civilization talks to itself using the sky. That shell has been growing at the speed of light, a soft sphere, about 100 light-years in radius. Within it, any patient listener with a big enough receiver could, in theory, notice that one small planet is noisy. Our oldest broadcasts have already washed past stars like Arcturus and Aldebaran, slipping by without any way to know if anyone was there to hear them. They have also swept across the orbits of dozens of known exoplanets, worlds with names like Ross 128b or Gliese 667 cc, some sitting in zones where liquid water might be possible. Most of those stars are still far away, distant lanterns in the dark, but one group sits closer than any other, the triple system we call Alpha Centauri. Because it is our nearest stellar neighbor, our thoughts keep circling back to it when we whisper about the first true interstellar journey. Alpha Centauri is not a single star, but three. Two of them are bright, sun-like suns bound together, circling a common center of mass. Seen from Earth with the naked eye, their light blurs into one. Over about 80 years, the pair move around each other on an elongated path, sometimes coming closer than the distance between our Sun and Saturn, sometimes drifting farther apart, but always tied by gravity. The larger of the two main stars is called Alpha Centauri A. It is a touch more massive than our Sun and slightly larger in radius. Its surface temperature and color are similar to ours, a soft yellow-white, but it shines more intensely, putting out roughly half again as much energy. If you could stand on a world at the right distance from Alpha Centauri A, your sky might be brighter than an Earth day, your shadows sharper. So far, no confirmed planet has been found in a comfortable orbit there. But there are hints, faint suggestions in infrared data that a planet-sized companion may exist, somewhere at roughly the distance Earth keeps from the Sunday. For now, that possibility waits quietly for sharper eyes like the James Webb Space Telescope or future instruments on the ground to test it. Its companion, Alpha Centauri b, sometimes called Toliman, is a little smaller and cooler than our Sunday. Its surface glows with a warmer, more orange light, and overall, it radiates less energy, more like a cozy hearth than a blazing lamp. Yet in high-energy X-rays, it is surprisingly lively, more active than many stars of its type. Observations show that flares in bright regions often ripple across its face, revealing a magnetic personality that can surge and quiet over time. For a while, astronomers thought they had found a small planet very close to Alpha Centauri b, circling once every dozen days. The idea came from delicate measurements of the star's subtle motions, tiny tugs that might hint at an orbiting world. But later, when the data were reanalyzed, a mathematical mistake came to light. What seemed like the heartbeat of a planet turned out to be an echo of noise and processing. The candidate faded back into uncertainty, a reminder of how careful we must be when listening for tiny signals in a restless universe. The third member of the system is very different. It is a dim red dwarf, much smaller than the Sun, with a surface barely warm enough to glow deep red. It shines at less than 1% of the Sun's brightness. This star is called Proxima Centauri, the nearest Centauri, because it happens to be slightly closer to us than its brighter siblings, by just a fraction of a light year. Proxima lies far from the central pair, thousands of times farther from them than Earth is from the Sunday. It moves slowly in a wide, long-period orbit around the system's shared center of mass, taking hundreds of thousands of years to complete one loop. From Proxima's vantage point, Alpha Centauri A and B would be bright twin stars, while our Sun would appear as a modest, pale point among many. Unlike the two larger stars, Proxima has at least 2 confirmed planets and the hint of a third. Around this small, cool star, the search for nearby potentially habitable worlds becomes less abstract and more tangible. The first discovered planet, Proxima Centauri b, orbits very close to its star, only a fraction of the distance between Earth and the Sunday. It takes a little more than an Earth week to complete one full circle. Even so, because Proxima is so faint, the amount of heat Proxima b receives is in the same broad range as what Earth gets. Estimates suggest that, averaged over its surface, the planet might be cold, but not hopelessly frozen, with temperatures that could, under the right conditions, allow liquid water to exist, somewhere, perhaps in a band or patch. But closeness to a red dwarf comes with trade-offs. At such a short distance, tidal forces likely keep Proxima b locked, with one face always turned toward its star, much like the Moon always shows one side to Earth. One hemisphere may live in endless daylight, the other in permanent night, with a thin line of twilight between. A sufficiently thick atmosphere and oceans could spread heat around, smoothing the harsh contrasts, but that depends on whether the planet managed to keep such an atmosphere at all. Proxima itself is a flare star. Its magnetic fields can twist and snap, releasing bursts of radiation and charged particles that wash over its planets. Over long timescales, those flares might erode the upper layers of atmospheres, peeling them away into space. A strong planetary magnetic field could help shield the air, but we know nothing yet about Proxima b's core or rotation beyond the bare fact of its tug on the star. So the planet hovers in possibility. Maybe a bare, bombarded rock. Maybe a world that stubbornly held on to air and water despite the temper of its sun. Farther out, on a much wider orbit, lies Proxima Centauri c. It takes several Earth years to go once around the star and receives very little warmth. With a mass several times that of Earth, it probably belongs either to the family of super-Earths, rocky worlds larger than our own, or to the class of mini-Neptunes with thick envelopes of gas. At such a distance from a cool star, its surface, if it has one, would be extremely cold. deep in the realm of frozen gases. Some observations have even hinted that Proxima c might possess a broad ring system, which would spread its reflected light into a halo around the planet. But this suggestion remains tentative, like so many early glimpses. Closer in than Proxima b, at an even tighter orbit, there may be a third, smaller planet, Proxima d. The signal is delicate, right at the edge of what our best instruments can distinguish, suggesting a world with a fraction of Earth's mass circling the star in just a handful of days. If it exists, its surface would be hot, likely too hot for comfortable liquid water, more akin to a baked, glowing rock than a gentle oasis. For now, it is a candidate, not a certainty, a tiny rhythm in the data that needs repeated listening. When you picture all of this together, Alpha Centauri becomes less a simple nearest star and more a little community. Two bright suns dancing close, a dim red ember circling far out, and at least two, maybe three, planets holding tight to that ember's faint light. Somewhere out there, our oldest radio waves are just beginning to tickle that system, a faint background hiss that says, without trying to, someone is speaking here. The distance between us, though, is still immense. Light itself, the fastest thing we know, needs more than 4 years to cross the gap. Our present-day spacecraft, swift by our standards, would take tens of thousands of years to drift from the Sun to Proxima. In human terms, that is longer than most of recorded history. And yet, minds keep returning to the question, could we ever send something small but purposeful across that gulf within a single human lifetime? One idea that has captured imaginations is called breakthrough starshot. Instead of a single large ship, it imagines a fleet of tiny probes, each no larger than a small coin or a thin card, packed with miniature cameras and sensors. These starships would not carry fuel in the usual sense. Instead, each one would be attached to a delicate, reflective sail, thinner than a human hair and spread out like a bright petal. From Earth, a powerful array of lasers would shine on the sail, pushing it with light alone. At first, the pressure would be gentle, hardly noticeable. But over minutes and hours, the continuous push could accelerate the tiny craft to a significant fraction of the speed of light, perhaps around 20%. At that speed, the journey to Proxima Centauri would shrink from tens of thousands of years to roughly 2 decades. The probes would not slow down when they arrived. They would rush through the outer reaches of the system in a quick, fierce flyby, snapping pictures and sampling starlight in the short time they passed near the planets. Their data, compressed and beamed back as bursts of radio waves, would then spend several more years crossing the distance home. On a human timescale, such a mission would still be slow. A person alive at launch might be old or gone by the time the first detailed images returned. But on the timescale of stars and orbits, it would be like skipping a stone across a pond, brief, light, and full of meaning. Somewhere in the dark between our Sun and Alpha Centauri, the edge of Earth's radio bubble is moving outward, carrying our unintentional messages into the quiet. And somewhere in our own imaginations, small sails are already unfolding, catching not wind, but light, preparing in thought for a journey we have not yet made with metal, but which we have already begun with questions. Before you can imagine a real journey beyond the comfort of our own system, you have to decide where, exactly, your thoughts would like to land. Among thousands of discovered worlds, which one feels most like a distant cousin of Earth, and which are simply too strange and hostile to hold anything we'd recognize as life? Scientists needed a gentle, systematic way to sift through this growing crowd of planets. Something more precise than, "This one looks nice." So they created a kind of scorecard called the Earth Similarity Index, ESI for short. It is not perfect, but it gives us a way to say, if Earth is our reference point, how closely does this other world resemble it? The index uses a few key ingredients: a planet's radius, its density, and its average surface temperature. Together, those numbers let us estimate its mass and guess at what it is mostly made of: rock, gas, ice, or some mixture. From there, we can infer how strong gravity might feel at the surface, whether a planet is likely to hold on to an atmosphere, and whether liquid water could exist openly rather than being locked into ice or boiled off into vapor. In this scheme, Earth is assigned an ESI of 1. It is the benchmark, the just right world by definition. Every other planet or moon is compared to that standard and given a value between 0 and 1, with higher numbers meaning a closer resemblance in those basic physical ways. Most of the worlds we know, both in our solar system and beyond, end up with low scores. Anything with an ESI below about 0.5 belongs to the least promising category. These are mostly gas giants, icy balls far from their stars, or searingly hot worlds hugging too close to their suns. Even if one parameter looks appealing, a single extreme value elsewhere can quietly ruin the chance for Earth-like conditions. Venus is a good example of how deceptive numbers can be. On paper, it looks like Earth's twin. Its radius and mass are very close to ours. Its gravity would feel familiar under your feet. But Venus orbits closer to the Sun, and it wears a thick, insulating coat of carbon dioxide and clouds. Trapped beneath that blanket, heat builds up relentlessly. The surface becomes a furnace, hot enough to melt lead, the air heavy and crushing. So even though Venus looks like a sister from far away, its ESI is low, and any hope of life on its surface, at least in a form like ours, evaporates in the heat. Planets and moons with ESIs between about 0.5 and 0.7 make up a middle group. They resemble Earth more than the gas giants do. Many are rocky, with temperatures that might be moderate in some regions. Some could be ocean worlds, bearing deep global seas. A few large satellites, such as those around giant planets, might fall into this range as well. These worlds invite attention, but a higher ESI on its own does not guarantee comfort or life. A planet can be the right size, but too light to hold a thick, protective atmosphere. Without enough air, harmful radiation from its star or from space can strike the surface directly. Another planet may be locked tightly to its star, showing only one face to the light. On such a world, one hemisphere could be a scorched desert and the other a frozen night, with a narrow, possibly stormy band in between. All of these details matter, and the ESI can only hint at them. The rarest group contains worlds with an ESI higher than about 0.7. These are the ones that, on paper, come closest to matching Earth's size, density, and temperature. None of them live in our own system. They are all exoplanets, circling other stars. Among them, one stands out in particular, not only for its high score, but also for its gentle distance. A planet we call Teegarden B, just over 12 light-years away. Teegarden B orbits a small, dim red dwarf star known as Teegarden Star, discovered only in the early 2000s. This star is not a bright lantern in our sky. It is more than 1,000 times fainter than the Sun, too faint to see with the naked eye, even though it lies relatively close to us in galactic terms. Its mass is less than 1/10 of the Sun's, and its radius is only a little larger than that of Jupiter. Deep inside, nuclear fusion trembles along at a low rate, just enough to keep it glowing. Its surface temperature is around 2,900 Kelvin, far cooler than the Sun's, so it shines in a steady, reddish light. For a star this small and gentle, the region where temperatures are right for liquid water, the so-called habitable zone, sits very close in, like a thin ring drawn just above the star's surface. In 2019, astronomers watching Teegarden's star noticed tiny, regular wobbles in its motion, caused by the gravitational pull of orbiting planets. From those subtle tugs, they inferred the presence of at least two worlds. One lies outside the habitable zone, too cold. The other sits right within it. The outer planet is called Teegarden C. It travels on a nearly circular path, taking a bit more than 11 days to complete one orbit. It is probably a rocky world, only slightly more massive and slightly larger than Earth. But because Teegarden's star is so faint, Teegarden C receives much less energy than we do, well under half of what Earth gets from the Sunday. Its average surface temperature would likely be well below the freezing point of water, making its surface, if exposed, harshly cold. Still, cold is not the same as empty. It is possible that beneath a thick, icy crust, Teegarden C might hide deep oceans of salty water, warmed from below by the planet's interior. In our own system, several moons of Jupiter and Saturn show that liquid water can persist in such hidden layers, insulated from the vacuum above. If something similar happens on Teegarden C, its seas would be locked away, unreachable from space, but perhaps quietly active in the dark. The inner planet, Teegarden B, is the one that has captured the most attention. According to the Earth Similarity Index, it has a score of about 0.95, just a small step below the perfect reference value of Earth, that is closer than any other known world. Teegarden B orbits much nearer to its star than we do to the Sun, at roughly a quarter of Earth's orbital distance. Because the star is so faint, that close-in orbit still falls within the habitable zone. The planet circles Teegarden's star in about 5 days, following a path that is nearly circular, which means it does not swing wildly between hot and cold extremes during its year. In terms of energy received, it gets modestly more than Earth does, enough to warm it, but not enough to guarantee a runaway greenhouse, at least in simple models. Estimates suggest that Teegarden B's mass is only a little higher than Earth's, and its radius differs by just a small fraction. If you could stand on its surface, the pull of gravity beneath your feet would feel very similar to what you are used to, perhaps just a touch heavier. That makes it reasonable to imagine that its interior might resemble our own worlds. A dense, metallic core, wrapped in a thick, rocky mantle, and a relatively thin crust of solidified rock on top. Basic modeling of the balance between incoming starlight and outgoing heat suggests that Teegarden B's average temperature might hover around a few degrees above Earth's global average, warm enough to allow liquid water to exist openly, at least in some regions, if the atmosphere cooperates. For many microorganisms and simple forms of life, such conditions would be comfortable rather than extreme. But again, the atmosphere is the great unknown. The method used to detect Teegarden B watching the star's motion does not reveal what kind of air, if any, the planet has. A thick atmosphere rich in greenhouse gases like carbon dioxide and methane could trap more heat, raising temperatures and perhaps pushing the planet towards steamy, cloud-wrapped conditions. On the other hand, if clouds were highly reflective, or if the atmosphere were thin and poor in greenhouse gases, the surface might end up cooler than simple estimates suggest. Being so close to its star, Teegarden B is likely tidally locked, always showing the same face to the light. One hemisphere would live in perpetual day, staring into a reddish sun that never sets. The other would be buried in endless night, its only illumination coming from starlight and, perhaps, faint auroras. The boundary between these halves, the twilight ring, might host strong winds as warm air from the day side tries to flow into the cold darkness. Teegarden's star, like other red dwarfs, is known to flare. Sudden bursts of radiation can temporarily brighten it, changing the amount of energy that reaches close-in planets and bathing them in high-energy particles. Over long spans of time, such activity might nibble away at a planet's upper atmosphere, especially if its magnetic field is weak. Yet even these challenges do not entirely close the door on the possibility of life. If Teegarden B has oceans, water could act as a shield, absorbing harmful radiation before it reaches the depths. Life, if it appeared, might thrive not on sunlit continents, but in dim underwater environments, warmed by the planet's interior and gently stirred by currents that distribute heat from the day side to the night. We know from our own world that life can be surprisingly tough. Creatures have been found near undersea volcanic vents, in frozen brines, in acidic pools, and in rocks deep below the surface. Given enough time and the right chemistry, even a small pocket of calm, protected water could be enough for something simple to begin. So when scientists look at Teegarden B's high Earth Similarity Index, they do not imagine an exact twin with familiar forests and blue skies. Instead, they see a world where some of the basic physical conditions, size, gravity, temperature, line up just enough that, with the right atmosphere and the right history, life might have had a chance to light a tiny spark. And sometimes, in the long story of a universe, a tiny chance is all it takes for something new to begin. Life, as far as we know it, is one of the quiet miracles of the universe. It is intricate, delicate, stubborn, and still deeply mysterious. We have been surrounded by it for as long as humans have existed, yet even now, some of the most important questions remain unanswered. One of them lingers at the edge of almost every cosmic story. Is life something rare and unlikely, a fragile flame that flickered to life only here? Or is it a natural outcome wherever the right conditions last long enough? So far, we only know one world where life definitely exists. That makes it hard to tell whether Earth is a strange exception or an example of a common pattern. It is no wonder that the search for life beyond our planet has become one of science's most tender and persistent quests. To even begin that search, we need a way to look at distant worlds and ask, how welcoming might this place be? One simple tool for that is the Earth Similarity Index, adapted here in a very stripped-down form. Think of it as a quick checklist, built from a few things we can usually measure about far-off planets: their size, their mass, their orbit. From those, we can estimate how strong gravity would be at the surface and what the planet's equilibrium temperature might be, the rough balance between heat received from the star and heat radiated back into space. Those two factors alone, surface gravity and temperature, already tell us something important. Gravity hints at whether a planet can hold on to an atmosphere thick enough to protect and nourish any future life. Temperature suggests whether liquid water or some other fluid could remain stable on the surface instead of freezing into stone or boiling away. It's a very basic filter, but for exoplanets, we often have little more to work with. The beauty of this simple version of the index is that it can be calculated as soon as we know, even roughly, a planet's orbit, mass, and radius. But its simplicity is also its weakness. Life depends on more than just gravity and warmth. So, in imagination, we can gently expand this checklist, keeping its heart, but adding a few more questions that matter. One of those questions concerns the parent star itself, a star that flares often, sending out blasts of high-energy particles and radiation, can strip atmospheres from planets that huddle too close. Red dwarfs, for example, are small and long-lived, which is good. They can shine steadily for tens or hundreds of billions of years, but many of them are also temperamental, with frequent flares that can batter nearby worlds. On the other hand, very massive stars, like brilliant blue-white giants, live fast and die young. Their lifetimes are so short and their radiation so fierce that there may not be enough time or calm for complex chemistry to settle into something as delicate as life. Somewhere between these extremes lie the more modest orange and yellow stars, like our Sun, whose light is steady, whose lifetimes are long, and whose radiation is intense, but not overwhelmingly destructive. For our expanded index, stars of this kind are gentle lanterns, especially favorable hosts. Another question we must ask is, how close is the planet to its star? Distance sets the first draft of the temperature, but it also controls the likelihood of tidal locking. Worlds that orbit very near often become like the moon around Earth, always showing the same face to their star. That creates a sharp contrast between the endless day side and the endless night, with extreme temperature differences, unless an atmosphere and oceans can move heat around. Move too far away, though, and the planet slips out of the habitable zone altogether into a realm where the surface may be permanently frozen. The sweet spot is narrow and depends on both the star's brightness and the planet's own atmosphere. Our index quietly prefers orbits where temperatures are neither relentlessly boiling nor forever locked in ice. Composition matters as well. Hypothetical life, as we currently imagine it, needs certain chemical elements: carbon, hydrogen, oxygen, nitrogen, phosphorus, and a scattering of metals like iron. It also seems to want surfaces, interfaces, where rock, liquid, and air can meet and exchange. Rocky planets and super-Earths with solid crusts are good candidates. Mini-Neptunes with thick envelopes of gas and no true surface are harder to picture as homes. Ocean planets with deep, global seas may be lacking in exposed rock and certain nutrients, making life possible but perhaps less diverse. With these extra questions in mind, star type, distance and tidal locking, and planetary composition, we can build a gentler, more complete picture of how welcoming a given exoplanet might be. Earth, unsurprisingly, looks very beautiful in this scheme. Its gravity is comfortable, its temperature range mild, its star calm enough and long-lived, its composition rich in the chemistry we know. Mars, by contrast, starts well, but falters. It is rocky and not too far from the Sun, but it is small and light. Its gravity is too weak to hold a thick atmosphere for billions of years, and it has lost most of its surface water. Even though Mars scores well on some measures, its cold, thin air, and dryness make life on its surface, especially complex life, struggle to gain a foothold. Venus, from another angle, looks almost perfect in terms of size and composition, yet a runaway greenhouse effect has turned it into a world of crushing pressure and dangerous heat. Most of its parameters might sit comfortably in the green range, but the extreme temperature cancels out those advantages for life at the surface. Looking only within our own system, then, we must admit that there is no true twin to Earth, no second cradle with both the right physics and the right climate. Beyond the familiar planets, however, the sky has revealed more than 5,000 exoplanets so far, orbiting stars scattered across our corner of the galaxy. Some of them, at least on paper, come surprisingly close to the conditions we know. One such world is Gliese 1002b, a planet circling a small red dwarf star just a little more than 15 light-years away. It was discovered recently by watching the tiny back-and-forth motions of its host star shift so small that only very sensitive instruments can see them. These motions betray the gravitational pull of orbiting planets, letting us infer their presence even when we cannot see the planets themselves. The star at the center of this system, Gliese 1002, is much smaller and dimmer than the Sunday. Its mass is only a fraction of ours, its radius not much larger than that of Jupiter, and its surface glows at a relatively cool temperature for a star. Because of this, its total light output is hundreds of times weaker than the Sun's. From any planet at Earth's distance, Gliese 1002 would be a faint red ember in the sky, not the bright disk we are used to. Interestingly, this star seems calmer than many red dwarfs. Its surface shows fewer wild flares and violent outbursts than we often see in others of its kind, at least in the observations we have so far. That serenity is promising. It suggests that close-in planets might not be as relentlessly bombarded by radiation as they would be around a more active dwarf. Because the star is so faint, its habitable zone lies very close in, like a tight ring around a candle flame. Gliese 1002b orbits near the outer edge of this ring. It completes one full circuit in about 10 Earth days, which tells us its orbit must be much smaller than ours, only a few % of the distance between Earth and the Sunday. At such proximity, the exoplanet is almost certainly tidally locked, always presenting the same hemisphere to its star. Even so, the energy it receives from Gliese 1002 is only about 2/3 of what Earth receives from the Sunday. Simple calculations suggest an average surface temperature colder than our own, but slightly warmer than Mars. If the planet has a decent atmosphere, greenhouse warming could bring the day side into a range where liquid water might exist in patches or seas. The mass and radius of Gliese 1002b appear to be only slightly greater than Earth's, by less than 10% in mass and just a few % in size. That means surface gravity would feel very familiar, and the density points strongly toward a rocky composition. In our extended index, those are gentle marks in its favor. Its Earth similarity score is high enough that it sits comfortably in the most promising category. Climate models, even simple ones, hint that the hemisphere facing the star could host an ocean of liquid water, ringed by archipelagos or larger continents of ice and rock-covered land. Heat, transported by air and possibly by currents, could keep the Terminator region, the boundary between day and night, relatively mild, even if the dark side remains locked in deep cold. The star's gravity, tugging on the planet, may also stir its interior, providing warmth from within that helps keep an unseen subsurface ocean liquid even far from the light. Gliese 1002b does not circle its star alone. A second planet, Gliese 1002c, orbits farther out, taking roughly twice as long to complete a loop. It receives only a fraction of the energy that Earth does, making its surface, if exposed, bitterly cold. This outer world is more massive than Earth and that extra weight might drive strong internal activity. Tidal forces and radioactive heating could warm its depths, melting ice below the surface. It is easy to imagine a thick shell of frozen material above, with a deep, dark ocean beneath, rich in dissolved chemicals and shielded from harsh radiation by kilometers of ice. In that sense, Gliese 1002c could resemble the icy moons of Jupiter or Saturn, where our own probes have found evidence of hidden oceans and active chemistry. On such worlds, life, if it ever appears, would not sunbathe under a blue sky. It would live in the dark, near vents and hot cracks, feeding on the slow, steady energy leaking from the planet's interior. When we fold all of this into our quietly expanded index gravity, temperature, star type, orbital dance, and composition, we begin to see that Earth-like is not a single sharp category, but a landscape of possibilities. Earth remains our warm, familiar reference point. Mars and Venus fall short in different, instructive ways. Worlds like Gliese 1002b and c linger at the edge of our understanding, close enough in some respects to invite curiosity, different enough to remind us that life, if it exists there, could be far stranger than anything we have yet met. Among the forest of distant worlds we've discovered, not all are frozen deserts or scorched rocks. Some are warmer, gentler to imagine places where, if you close your eyes, you can almost picture yourself standing on an unfamiliar shore under the light of another sun. One of those worlds is K20-72e, more than 200 light-years away. It circles a small red dwarf star that is much lighter than our Sunday. This star is only a fraction of the Sun's size, its surface cooler, its glow softer, more orange-red than white-yellow. It isn't a blinding beacon like our Sun, but a steady ember burning in the dark. K20-72e was discovered by the Kepler Space Telescope. From far away, Kepler did not see the planet itself, only a slight, rhythmic dimming in the star's light. Every 24 days, the star's brightness dropped a tiny bit and then returned to normal. That regular dip is the subtle shadow of a planet passing across the star's face. From that pattern, astronomers worked out the orbit. K20-72e travels very close to its star at only about a tenth of the distance between Earth and the Sunday. At first glance, that sounds like a recipe for a furnace, but because the star is so faint, K20-72e actually receives only a little more energy than Earth does, about 11% more. In simple climate models, if this planet has an atmosphere similar to ours, its average surface temperature might sit in the low 20 Celsius, just a bit warmer than Earth's global average. Warm enough for comfortable liquid water, not so hot that everything boils away. Because it orbits so near, K20-72e is very likely tidally locked, or at least close to it. One hemisphere probably faces the star almost all the time, living in an eternal day, while the opposite side lies in permanent night. On the day side, the star might hang fixed in the sky, a reddish disk that never rises or sets, only slowly brightening and dimming with the star's natural moods. On the night side, stars would stand in a motionless vault of darkness, untouched by dawn. If K20-72e has a thick atmosphere and deep oceans, winds and currents could help carry heat from day to night, smoothing out the harshest contrasts. In that case, there might be a broad ring around the twilight zone, a band where the light is slanting and soft, where it is neither blazing nor frozen. In that gentle belt, oceans could stay liquid, and shorelines could exist under constant, dim sunset light. K2O-72e is slightly larger than Earth. Its diameter is about a third bigger, and its mass roughly a bit more than twice ours. That combination makes surface gravity stronger, perhaps around 30% higher than what you feel standing on Earth. If you could walk there, every step would demand a little more effort. Jumping would be harder. Your body would feel noticeably heavier. Yet, that same gravity helps the planet cling tightly to its atmosphere, making it easier to keep a dense, protective blanket of air. With this size and mass, K2-72e is very likely a rocky super-Earth, a world with a metallic core, a thick silicate mantle, and a solid crust, rather than a puffy gas planet. Somewhere on its surface, water could collect into lakes, seas, or wide oceans. Its atmosphere, if it exists, might carry nitrogen, water vapor, carbon dioxide, and a whole library of organic molecules slowly brewed by the light of a red dwarf. On a simple Earth similarity scale, K2O-72e ranks high, with a value close to 0.87 out of 1. It is not an identical twin, but it stands among the most promising cousins we've found so far. The terrain of such a planet might be relatively gentle: overall broad plains, rolling highlands, shallow basins, landscapes that help stabilize climate, let rivers wander, and give oceans calm places to rest. But no world gets every gift. The red dwarf at the heart of this system, like many of its kind, may be erratic. It can send out sudden flares, bursts of charged particles, and high-energy radiation. Those storms can erode atmospheres, especially on planets that orbit close in, and they can bathe surfaces in light that is anything but gentle. This is one of the main threats to any fragile biosphere. To endure that kind of weather, K2O-72e would likely need two natural shields: a strong magnetic field and deep water. A hot, rotating metallic core could generate a magnetic field that stretches far into space, deflecting many of the star's energetic particles. The ones that slip through would be guided toward the poles, where they would collide with the upper atmosphere and paint the sky with glowing curtains of light. On such a world, auroras might not be rare polar treats, but frequent, immense displays, veils of red, violet, and blue-green winding across the permanent night side. Oceans, too, offer protection. Water absorbs radiation and softens temperature swings. Life that begins beneath the surface of a sea is naturally shielded from many of the star's harsher moods. If K2O-72e has broad oceans, they could act as a cradle for any early living chemistry. The light that falls on those oceans would look different from what we know. Red dwarfs emit more red and infrared light and less blue and ultraviolet than the Sunday. If something like plants ever evolve there, their photosynthesis may need to adapt to that spectrum. Instead of green forests, K2O-72e might grow dark, purple, or deep red vegetation, tuned to drink in the energy of a ruddy star. Fields of alien plants could spread beneath a salmon-colored sky, their leaves absorbing the light we can barely see. High radiation levels and frequent flares could also shape the bodies of any organisms that live on land. Many might prefer to hide in soil, under rocks, or beneath water by day, emerging only during quieter intervals. Others could evolve thick skins, shells rich in protective pigments, or incredibly efficient DNA repair systems. On Earth, tiny water bears, hardy bacteria, and certain fungi already show us how life can adapt to extremes, surviving high radiation, desiccation, and cold. They are small, patient hints that biology can be tougher than our first assumptions. The star that K20-72e circles does not host only this one world. Astronomers have identified 3 other planets in the system. 2 of them, K20-72b and K20-72c, huddle even closer to the star. They are only slightly larger than Earth, but their orbits are so tight that any early atmospheres they might have had were probably stripped away long ago by fierce stellar winds and flares. These worlds could be bare, baked rocks, more like overcooked versions of Mercury than gentle places for water and air. The 4th planet, K20-72d, lies farther out, near the inner edge of the star's habitable zone. It is similar in size to Earth, but it receives much more energy than our planet does. Its surface conditions might resemble a milder Venus, hot, wrapped in a dense greenhouse atmosphere, perhaps covered in clouds that trap heat and reflect light. If so, liquid water on the surface would be unlikely to last. Any oceans might have boiled away into a heavy, suffocating sky long ago. Even so, the K20-72 system remains a quietly compelling destination in our imagination. A small, cool star at the center, 4 rocky planets circling in close, and among them, one, in particular, K20-72e, that seems to sit in a narrow band of just warm enough. Its size, mass, and estimated temperature all brush close to values we know. Astronomers are still studying this system, refining their measurements, improving their models, and listening for subtle signals that might tell us more. Each new observation adds a little shade, a little depth to the picture. And somewhere underneath those numbers and graphs is a simple human wondering. If there is a rocky shoreline under the red light of K2-72e's star, if waves are quietly shaping its stones, is anything alive there to feel the passing of time, unaware that far away another species is whispering its name into the dark? Among the worlds we've been imagining, some are similar in size to Earth, and others are much larger, with gravity that would make your knees ache just to think about it. For us, such places might feel punishing, but life itself is not as fragile as we are. On our own planet, living things have learned to endure crushing pressures in the deep sea, thin air on high mountain peaks, and temperatures that swing from baking hot to bitterly cold. Given enough time, biology has a way of finding footholds, even in heavy, unfamiliar conditions. High gravity, while challenging for human bodies, may simply become another constraint that shapes the bodies and behaviors of whatever grows there. If you let your attention drift about 1,800 light-years away from the Sun, you come to a star that feels strangely familiar. It is a yellow dwarf, very much like our own star, classified as a main sequence sun steadily burning hydrogen in its core. This star is called Kepler 452. It is only a little larger and more massive than our Sun, just a few percent heavier, a bit broader, but its light and color would look almost the same, a warm, white gold glow. Under that glow, an intriguing planet circles quietly, Kepler 452b. In 2015, astronomers using the Kepler Space Telescope noticed that Kepler 452's light dipped ever so slightly at regular intervals. Every 385 days or so, a small portion of the star's light was blocked. Those gentle, rhythmic shadows revealed the presence of a planet crossing in front of the star from our point of view. From the timing and depth of those dips, researchers calculated that Kepler 452b orbits at about 1.04 astronomical units, just a touch farther from its star than Earth is from the Sunday. One orbit takes it a little longer than an Earth year to complete. This distance is important. It places Kepler 452b comfortably in the star's habitable zone, the band where temperatures can, in principle, allow liquid water on the surface. It is also far enough out that the planet is very unlikely to be tidally locked. Instead of one side forever facing the star and the other locked in darkness, Kepler 452b probably spins, bringing day and night to most parts of its surface in a regular rhythm. Sunrises and sunsets would still exist here. Shadows would move, and the sky would change. Kepler 452b is not just another Earth-sized world, though. Estimates suggest that its mass is about 5 times Earth's, and its radius around 1.5 times larger. Those numbers imply that gravity at its surface is more than twice as strong as what you feel right now. A person used to Earth's gentle pull would find it hard to stand up, harder still to run or jump. Hearts would work overtime, muscles would tire quickly. But for native life born and evolved under such a pull, this would simply be normal. Everything from the height of cliffs to the shape of trees would quietly reflect that stronger grip. Such strong gravity has consequences beyond how things feel. It helps the planet hold a dense atmosphere over long periods, and it tends to smooth the landscape. Very tall mountains and deep, narrow chasms are harder to sustain when rock is pulled down so firmly. Over geological time, slopes slump, peaks erode, and basins fill. The result could be a world with gentler relief, wide plateaus, low rounded hills, and an abundance of shallow basins that may fill with water. Kepler 452b also receives slightly more energy from its star than Earth does from the Sun, about 10% more. In simple climate models, that difference nudges its average surface temperature upward to around 27 degrees Celsius, warmer than Earth's global mean. You can imagine a world where ice is rare outside the highest elevations, where many regions are humid and mild, and where seasons might feel more like an extended, lush spring or a long, warm summer. But that extra energy, combined with the right atmospheric composition, could also push the climate in a more dangerous direction. A dense blanket of greenhouse gases, too much carbon dioxide, too much water vapor, might trap additional heat, gradually warming the planet past a comfortable point. If feedback loops took over, the oceans could begin to evaporate faster than they are replenished. More water vapor would then enter the atmosphere, increasing the greenhouse effect still further. It is possible that Venus underwent a similar runaway process long ago, transforming from a potentially gentler world into the hot, suffocating planet we see today. For Kepler 452b, the outcome depends on details we do not yet know. How much carbon is stored in rocks and oceans, how active its volcanoes are, how reflective its clouds and ice might be. For now, we hold both possibilities in mind: a warm, water-rich world, or a supersized Venus cloaked in thick, steamy air. Given its size and mass, Kepler 452b is usually classified as a rocky super-Earth, not a gas giant. Its interior is likely to contain a large metallic core surrounded by a deep mantle of silicate rock, similar in composition to Earth's, but thicker and under greater pressure. Because larger planets can trap more heat from radioactive elements, Kepler 452b may have vigorous tectonic and volcanic activity. Plates of crust might slowly drift, collide, and sink, recycling material and building chains of modest mountains. Volcanic eruptions could feed the atmosphere with gases, while fractures in the crust might allow heat and minerals to leak into oceans from below. High gravity would shape these processes. Mountains could rise, but they would collapse and spread under their own weight more quickly than on Earth. Deep chasms would be harder to maintain. Their walls would be prone to slumping. The result might be a planet dominated by broad uplands and extensive shallow seas. Instead of one world ocean with a few continents, Kepler 452b could be almost completely covered in water, with scattered archipelagos and island chains breaking the surface here and there. If you picture yourself gliding above such a world, you might see vast stretches of blue-green water, dappled with floating mats of life, or streaked with the white of wind-blown waves. The coasts would be complex and fractal, carved into countless bays and inlets. On the islands, thick forests could grow in the humid air, their canopies woven into living carpets of green. Because Kepler 452 is a yellow star with a spectrum similar to our Sun's, the light bathing these forests would be familiar. Plants there would likely make efficient use of the same ranges of wavelengths our own plants cherish. Their leaves might be green, perhaps with hints of blue or teal, where different pigments layer together. Fields of low, sturdy grasses and shrubs could spread between groves of stocky trees with broad, deep-rooted trunks built to withstand the pull of strong gravity and the push of strong winds. Animals, if they exist there, would grow to fit the rules of their world. A high-gravity planet discourages tall, spindly bodies. Bones and muscles must work harder to support weight. Creatures might tend to be shorter and more compact, with thick limbs and strong tendons anchoring them close to the ground. Running fast would be expensive in terms of energy, so many animals might move with a steady, powerful gait instead of bounding. Some evolutionary paths could favor internal skeletons, much like ours, built from dense bone or an analog. Others might lean toward external skeletons, tough, jointed shells somewhat like those of arthropods on Earth. On Kepler 452b, such exoskeletons could provide support and protection, helping creatures resist both gravity and the elements. The question of flight is a subtle one. Some exobiologists argue that on a world with more than twice Earth's gravity, powered flight would be extremely difficult. Lifting a body against that pull demands so much energy that only very small, very light forms, perhaps insect-sized, could manage it. Others point out that if the planet's atmosphere is dense enough, the air itself offers more lift. Large wings moving through thick air can generate substantial upward force, making flight easier than intuition suggests. It is possible that both views are true in different ways. Kepler 452b might host a sky filled with small, delicate flyers, gliding on updrafts between island cliffs, as well as larger gliders or short-range flyers that use dense air to their advantage. All of this is speculation. Of course, gentle guesses spun from what we know of physics and life's adaptability. Kepler 452b remains a faint blot in our data, a periodic dimming of a distant star, not yet a world we can see in detail. We do not know whether it has oceans, whether its atmosphere is thin or thick, breathable or toxic, or whether its surface is dotted with islands or wrapped in cloud from pole to pole. What we do know is that, by the basic measures we can make from a far size, orbit, temperature, star type, it stands out as one of the more inviting exoplanets discovered so far. It reminds us that Earth-like conditions might not be unique to our system, even if they are not common either. It gives us a place to point when we wonder where life might have taken a different path, under a different sky. While we wait for future instruments to sharpen our view of Kepler 452b and worlds like it, the search for life continues closer to home as well. We probe Mars for traces of ancient microbes in dried lake beds and buried ice. We examine the subsurface oceans of moons where warm, salty water sloshes in the dark beneath shells of ice. We listen for tiny changes in starlight when planets pass in front of their suns, and we parse those faint signals for hints of atmospheres and clouds. Each new telescope, each mission, adds to our ability to ask this question with more care. We are learning to read the fingerprints of gases like oxygen and methane in exoplanet atmospheres, patterns that, in some circumstances, could hint at biological activity. Bit by bit, what was once only dream territory is becoming a field of practical, testable science. Somewhere in this expanding map of worlds, we may eventually find a clear sign of life, a chemical imbalance too strong to explain by geology alone, a spectrum that whispers of photosynthesis, or even, someday far in the future, a deliberate signal. We do not yet know whether that first confirmation will come from a world very much like Earth, or from a stranger environment where life has learned tricks we have not yet imagined. For now, we live in the question. We float in the thin shell of air around our own world, sending machines to nearby planets, building bigger eyes to peer into the dark, and inventing new ways to listen. The constant growth of our technology does not guarantee an answer, but it steadily improves our chances of hearing one if it is there. As you lie in your own quiet corner of this one known biosphere, it can be strangely comforting to remember that we are already reaching outward with light, with radio waves, with curiosity. We may meet life that feels familiar, or life that seems almost impossible by our current standards, or we may find that we are rarer than we thought. One night, some year, the data may finally align in a way that leaves little doubt. Until then, we keep watching, keep listening, and keep letting our thoughts travel to places like Kepler 452b worlds that exist for now as distant shadows and gently hopeful maybes, waiting in the dark while we learn how to see them more clearly.